as I said, today we will spend all the time talking about this one topic, uh, which when I took this class as a student, it's a little bit confusing. So, so you can already train neural net on iPhone 12. That's even before this chip, but it would be more efficient. The machine learning chip that they put in, I'm sure they already do some training over there. Training and inference are already done on your phone. And I think all the phones, mobile phones company, I think most of the companies are also looking into that direction. I see, to be honest, I take pictures too, right? I photograph a bit, right? And to be honest, the integrating machine learning into the camera is pretty good. It's a pretty good idea because one thing I have to do whenever I take picture with DSLR is I need to develop the picture, right? And it is a process that take a lot of time. And when you have these machine learning accelerators that would kind of like improve your picture by gathering a lot of data and will automatically kind of like do that for you. It's pretty much a godsend, to be honest. Uh, yeah, so I was kind of excited when I learned about this uh, this morning. So today we talk about cache coherency. And before I begin the class, I would like to give a little bit of feedback on the exam, which is good job, everyone. You did really well on the exam for most of you. And please keep this up because the final exam will probably be the same difficulty compared to this midterm exam. And the markup PDF will be distributed tonight whenever I am basically done with like meetings today. Uh, if you have any questions, you can ask me. And if you're curious about why do I take certain points off, let me know. In the PDF, it won't be like pen markup, but I put it as a comment box so that it's a little bit more organized. So you can tell that's your handwriting. These comment boxes are mine. And then I'll basically put in how much points off that you're getting for each of the comment box so that you know the total. And if I make mistake on summing up your total grade, let me know. Right? And your grade's already posted. I'm not sure if you saw it on Canvas or not. Uh, I think most of you did like much better than you might have think. And for those of you who don't like answer to the question that give you 3 points, please do. I'm glad that I have the question about like that's 3 points that say, okay, so far, are there any topics that you like in particular? I'm glad that for some of you, you said, okay, this is kind of like opens up this Pandora box that you always assume it exists, but you don't know how it works. For those of you who tell me this class is a little bit too different from the class you've been taking so far, I also understand that. That's why I changed assignment 3 format this way. And apologize ahead of time. It's not out yet. I'll try to release it as soon as possible. But basically for the coding part, you're given the solution for assignment 2. Then you implement caching and implement branch prediction. The write-up would have all the information needed to do caching and branch prediction. You don't have to model the memory. Memory is still like magical. And then there'll be a written part. The written part is required. The coding part is all extra credit. So if you do the written part, I hope that you basically get prepared for your final exam. The due date of this will be the last possible day I can extend before I need to submit my the grade for the class to MUIC offices. And then grade for assignment 1 and 2 will be out as soon as possible. Any questions so far before we go through some recap of what we went through? All right, so let's do a quick recap. Multiprocessor, what is that? Basically, you put more than one processor on the chip, right? Similar to this new Apple chip, but then the new Apple chip not just put the CPU on the die, right? Multiprocessor, you're looking at like 4 CPU, 8 CPUs. Multiprocessor also include the case where you have CPUs and GPUs and things like the M1 chip that just came out, right? Basically, it consists of multiple processing unit. What is a processing unit? Things that consume your data, right? You feed them the data, and then it spit out the results. So you can add more processing core to get better power efficiency. Why is power efficiency important? You want to make sure your computer doesn't consume too much power. Otherwise, you need a nuclear power plant or your laptop would die within like 5 minutes. How to utilize multiprocessors? Obviously, you can run separate programs on each processor, right? Windows, Chrome, and Microsoft Word and PDF, right? You can run different threads of the same program. Let's say you have a parallel program, you can then use multi-threading to run your program across different processors. So key issues that we talked about last Monday, like this particular Monday this week, is how to share resources, how to prevent application to take out the resources. In particular, we talk about like, okay, what if you have integrated GPU? What if you have the system on chip that share the DRAM, right? This is exactly the same as the M1 processor, but M1 even have more things. Let me give you one more example with this Apple chip, right? They have the security chip that share the DRAM with the rest of the processor. What do they mean? The security chip would handle things like your fingerprint, ID, your password, right? So you need to protect that from everyone else, including the OS, right? Because the assumption is I can't trust anyone, including the operating system, the iOS. Why is that the case? How many of you are living in the age where we jailbreak iPhone? I think it was like 10 years ago. Anyone heard about jailbreaking iPhone? I'm sure you all like heard it at some point. Anyone still use a jailbroken iPhone? Okay, please not, to be honest, because basically jailbreaking, it means that you change the kernel code, you change basically the system software inside your phone. You have to really trust the guy who write that software to actually give your information to them, right? They have access to everything because they have kernel level privilege. But the security chip would assume that the user can jailbreak your phone and it should still be able to function and deal with your fingerprint data without leaking that data out, right? How do they do that? To be honest, I'm not going to cover it in this class because it requires a little bit more advanced knowledge on certain security topics plus the hardware topics. But you might find this series of topic interesting. There are resources you can read online. If you're curious about it, you can follow up after this class ends. Basically, after this semester ends, if you're curious about anything we cover, any technology we might have talked about, or any chip that came out, feel free to ping me. I would love to learn as well. Like whenever the new chip came out and student ask me, okay, what about this chip that came out? And I'm like, okay, I need to look it up because sometimes I don't hear about every single news. And these are exciting. Today, we'll talk about how to ensure data coherency. Not tomorrow, the next class, we'll talk about data consistency, unless we finish way before the class supposed to end. But I don't think that's the case. And then in the OS class, look, we're not going to cover it in this class. When you have multiprocessor, you need to talk about when to run things at what core, right? So it is thread scheduling, that's thread pool concept, the things that you hopefully love or hate from the OS class. So let's focus on what we want to talk today, how to ensure data coherency. Right? So the first question that you might have in mind is, what is cache coherence? So the thing with this, when you have a pointer, right, the same virtual address need to have the same data. It's the data that you're supposed to have the same single value for that, right? Or at least whenever the core demands the data, and whenever I want to read to that address, I should get the most updated version of that address. The problem with multiprocessor is you have the private L1 cache, you have the shared L2 cache, which means that if I'm writing to the private cache, right, I have the updated information in my own private cache, but I share that data with another processor. It means that the other processor don't see this updated data, right? Two apps want to read or write to the same cache line. The data might be in the private L1 cache, so I write to the private L1 cache. The private L1 cache of the other processor will not have this updated data. So our problem is, how do we keep track of this? How do we keep track of the case where I don't have my updated data? And how can I invalidate the data that I have? So that's basically the question, how to maintain coherency. Basically, coherency means that I will be able to see the most updated version of my data when I'm looking at my private cache. So how do we impose this in a high level idea? So right now, let's talk about high level idea before we dive deeper. High level idea is each cache line will have its own status. If the cache line is read only, what do they mean? It means I can read, I can access the data because the data is not modified. It's not modified. Everyone can access it, and you are guaranteed that's the most updated version of the data because the data is read only. So everyone have access to the data, and it will be the most updated version. Any questions so far? All right. So what if I have one processor, say P1, so let me write it this way, right? I have P1 and P2, processor 1 and processor 2. This is the L1 cache of P1, and this is the L1 cache of P2 that share this L2 cache, right? And let's say both of them access this address. Now let's say this address has a value of 4, right? So P1 and P2 would have the same value of 4 in their own private L1 cache. You can still see my writing, right? I know it's a little bit small because I ran out of room on what to draw here. Yes, no. Is it legible, what I'm writing? Or should I erase everything and make it bigger? Okay, awesome. So if this is legible, what if I say P1 modify this and change the value to 5? What will happen? P2 still see the value 4, right? So if I have to write to the cache line, I need to be able to inform P2 that, hey, that value is old. If you need the updated value, get it from me. This is called cache coherence protocol. Everyone with me so far? Basically, I have the updated value in my own private data. You need to make sure you inform everyone else who owns that address saying, hey, if you need to access that address, here's the most updated version of the data. The one you have is old. The goal of this coherency protocol, the goal is you want to minimize communication and data transfer, right? Data transfer. Why? Now I'm making a mess of my slides. So you want to minimize data transfer. These communication increase the time it takes to read your data. The data transfer also increase the time it needs to access your data. They also consume more power because you're moving things around. Whenever you have to move things around, that burns power, right? If you need to run from, let's say if I have to run from this room to the front of my house, right? I will burn some calories, which is a good thing for me because I'm fat, but For a laptop, right, you don't want to burn too much power because the battery would run out. So, cache coherence 101. There are multiple states that the cache block can take. Basically, it means that if there are writes to another processor, let's say I have the earlier example with the P1, right, and P2, there's a write to this address. This is the same address, address A, which is sharing, this is L2 cache, right? So this is address A. This is value 4, this is value 4, this is value 4, but P1 writes to A, this becomes 5, right? If this becomes 5, it means that I need to invalidate this value because this is not the legit value anymore. It means that the way to do this is I will have a bus that connects all my L1 cache, right? So that this bus is used to inform the other processor of your own action. This is called Snoopy bus. So what is snooping? What does snooping mean in English? So a lot of things we name in computer science we try our best to have the same analogy as the English meaning. So what does snooping mean? Anyone want to take a dictionary like Google search and look up what does snooping mean? Yes, getting information about other people, right? So let's say you have your ex snooping on your phone. It means that he or she is trying to get your information from your phone. A dog snoop around a lot, right? Because he or she, it will smell the surrounding area to basically gauge what's the environment around him or her. Uh, so we call this bus, which allows processor to get information that happened in a different processor. We call this a Snoopy bus, right? That's where it got the name from. So let's visualize it. Like, let's say you have cache block A, which has the value 4 over here, A value 4, A value 4, 4, my bad. I don't know why I write 5. I'm thinking ahead of myself. There'll be a bus between processor 1 and 2, right? The way it works typically is it'll be something like this. There'll be a bus that connects all the processor. And this is Snoopy bus. When I write to A, which changed the value from 4 to, let's say, 5. Basically, I say store new value from 4 to 5. This get replaced to 5. The other processor don't know this yet, but I'm gonna send a signal saying, hey, I write to A. So if I send this signal to everyone else saying, hey, processor 1 is writing to A, what will happen? What can processor do to make sure that it it knows that A is now outdated? You will invalidate, right, this data because you now know that someone is modifying it. So the copy that I have is old. If I need the copy, I need to get it all the way from here. But if I need to read it, I need to make sure this value 5 go down here as well, change to 5. Today, we will talk about how this happened and how to make sure that we will be able to get the correct data. So the first protocol that we will learn is called the MSI protocol, MSI Coherence protocol. This is not named after the motherboard company. It's coming from the state of the cache line. M stands for modified. S, share. I, invalid. Basically, each cache block can have one of these three states. Modify, which means that this is the only copy, no one else has it, and this copy is dirty. Share, it means that it might be one copy that you have it, you have not right to it yet, and people can have this copy as well. It's like read-only copy. Modify, dirty mean someone writes to it. In this case, the processor writes to that already. So if you have read miss, basically read cache, basically this is cache miss when you want to read the data. You send a read request and you transition to S. It means that originally it's invalid. This is now share because you read to it. If you have a write miss, you transition from invalid to modify. You send the read exclusive to everyone else. So if the processor see read exclusive, you invalidate your copy, and then transition from share to modify can be done without reading the data from the main memory. So let me draw this thing so that it's more clear. So let's say this is processor 1. This is processor 2. And you talk about address A. Right? Address A. Initially, I don't know why I write A inside the box. So this is address A. Initially, both of them are not in the cache. So let's say I have a read miss. Processor 1 want to read A. It missed because the data is not in the cache. You brings in the cache block, right? You bring in the cache block from the memory. Goes into here. A has the value, let's say it's 4. The state would now be share because from invalid, when you brings in the cache block, you will then transition yourself into a share state. Let's say processor 2 want to do the same thing. I want to load address A into my register, right? So you will then put this data in here. Or what is the state? If I transition from invalid, I'm reading, what do I transition to? Is it staying at invalid, move to share, or move to modify? I'm reading. Share, modified, or invalid. There are 3 choices. It should, so first of all, it should be valid now because originally it was invalid. I don't have the cache block. I load the data. Now I have the cache block. So from I, what do I move to? I have the cache block now. And I'm reading. So from I to actually to S because you are reading. So you transition to share. Basically, you now is in a share state. You see that processor 1 and 2 both are in the share state, right? And they both see the same value, 4. It with me so far? Any questions so far? Because I feel confusion. So please ask me the question. Let me actually use this diagram to explain the MSI protocol. Okay, so let me erase everything on this slide. I have a memory. And this is address A. Value is 4 right now. With me so far, right? That's address A. Value is right now 4. Then I say processor 1 read to A. These value 4 would get brought into, well, the shared cache, right? This is address A, as well as the processor L1 cache, address A. With me so far? Are you with me so far? Okay. The state originally, I'm gonna use a different color. So originally it was invalidated. Then when you have the value 4 in your cache block, now this changed to share. Why is it share? So the name might sound confusing, but essentially the reason why this is a share state is this is a copy that I have. It's the most updated copy, and I can share it with someone else. No one modified the value yet. So if anyone else want to read this address A, for example, processors who say I read A. What will happen is, well, you go look up in the cache and like, oh, okay, A is here. So you bring the data over to here, address A, share 4, right? This is the data. This is the state. Is share. Are you with me so far? The state share means that if I need to read this data, this is the safe data. I can read it. Every single processor will see this exact same copy. Are you with me so far? Basically now both 1 and 2 basically both of them has this address in the cache block and the value is 4. Both of the cache block is in the share state. So what do we do next? Let's say processor 1 now write value 5 to A, right? 5 into address A. What happened is now address A, the value 5 goes in here. This now changed to 5. Because you are writing, you modified it. The state would now change from share to modify. You send the signal to everyone saying, hey, I write to A. Send it to everyone, including processor 2. Processor 2 has a copy of A. So whenever processors who see this signal, what does it mean? When the processor 2 see the signal, hey, someone write to A, what does that mean? What does it mean to this copy that processor 2 have in its own cache? Yes, it becomes invalid because this is the old copy, so you have to invalidate it. You have to invalidate it. What does that really mean? It means that I cannot use that copy. The only way I can use this copy is if I then read. So what happened is, let's say I want to read A again. This is the green thing. So let me order this. Step 1 is in red, followed by step 2 in blue, followed by step 3 in green, right? So if you go look back at this slides, the order is red, blue, green. So now you read A. You look at this and like, okay, it's invalid. I don't have the current copy of the cache. What does it mean? It's a read miss. It's a read miss because my private cache, even though I have cache block here, is invalid. I cannot use it. I'm gonna go search here. This is also invalidated, right? Because you don't have the most updated copy, it means that now the copy right here has to write the value, correct it to 5. So this become 5. Once that is valid, so this is valid, then you are copying data over to here. Now this become 5. From invalidate, what do I change to? I'm reading. From invalid, what do I change to if I'm reading? share, yes. And then over here, because I write the data back already, the value 5 go to the share cache, the modified, because the block is not dirty anymore, I flush. So this process is called flush, right? So this becomes share. So now you see how each processor can share the data and they will have the most updated copy. You just need to make sure first you flush the data whenever some processor needs the data. The reason why we call it flush is basically we let the data drain down into the next level of my hierarchy so that I can see what is the most updated version of the data. Any question? So which phrase that we can change 4 to 5 in the memory? That actually depends, to be honest. Because right now the share cache has the most updated copy, right? So everyone will see will be able to access the most updated copy in the share cache. What is the only case that I will not have that cache block anymore in my share cache? Is when that block got replaced, right? It get kicked out. My share cache is too small, so sometimes this block will get kicked out of my share cache. Right? Are you with me so far? Basically, at some point, the cache block that contains address A will get kicked out from the share cache. By that time, you write to the main memory. If you go back to our caching lecture, there'll be this one bit called the dirty bit. Dirty bit becomes 1 if this happens. When dirty bit is 1, you know that you have to write this address in the main memory because someone modified it. So does it answer your question? It basically means that I'm going to delay writing. Why are we delaying? Well, because it's already in the share cache, everyone see this data anyway, so I can handle more writes without using the memory bandwidth, right? I prevent the block to be basically right back to the main memory. So that's a MSI coherence protocol. The problem of MSI is this. If you have a read, it goes directly to share, even though you might be having the only copy, right? If you are the only processor with the data, you're in a share state. If you are one of the multiple processor who has the data, still again share phase. This can potentially be done without modifying or letting other people know. Right? If you have the only copy and you read it again, do you have to send the read signal to everyone else? No. Right? So the better protocol is called MESI or MESI, stand for modify, exclusive, share, and invalid. MSI are the same. M is the only copy is at your private cache and the block is dirty. I modify that data. Exclusive means that, well, I have the only copy and I have not modified the data. Share is the same. You can be potentially owns one of the several copies of these data. Invalid means I don't have the updated version of the data or the cache line is not in the cache, right? So now if you write to the cache block and you are the only person with the data, you can transition from E to M without notifying anyone. Why is this good? You allow other people to use the Snoopy bus, right? So you don't have to utilize the bus. There are, if you look at this, right, there are two important operations: read and write. Write modify the data. Read needs to get the correct, most updated copy. So these are the two important things that you need to understand when you're trying to go through this protocol. If I'm reading, I better have the most updated copy of the data. If I'm writing, everyone else should be aware that their own copy of the data is now outdated because I modified the data. Any questions so far? Before we go to the diagram and some potentially examples. So these are the key issues. You want to make sure that when you write the data, you want to make sure everyone who want to read it get the most updated copy. At the same time, you want to minimize communication. The fewer time you use a Snoopy bus, the better, because every time you use it, you can potentially slow things down. Whenever you need to move data from the L2 cache to the L1 cache again, whenever you have to move from something to invalid, that also slow things down. So only update if you need to. If you don't need to update your data, you don't have to update it. Each cache block need to maintain these states. These are, what does the processor do? Do I read or do I write to cache block A? And what do I see from this shared Snoopy bus? Is someone else reading or writing to processor, basically to cache block A? So here are the protocol. I'm gonna draw it. Basically, there are four states: modified, exclusive, share, and invalidated. Right? So let's start with when you have when no one have the cache block. You are trying to read for the first time. Read for the first time. And let's say everything in the slide I would denote PR mean processor write, processor read. PW is processor write. SR mean you can see a Snoopy bus that someone read. SW means I look at the Snoopy bus and someone write to their cache, right? SR means that I look at the Snoopy bus, someone is reading that cache line. SW, I look at Snoopy bus, someone's writing to that cache line. PR means I am reading. PW means I am writing. So let's start by, I read this cache block. So that processor 1, processor 2, processor 3. Let's say we have 3 processors. Let's say P1 read this cache block A. Cache block A. For the first time. Initially you are here. Right? Initially you are in the invalidate. Why are you initially in the invalid? You never seen that cache block before. You are reading it for the first time. If I read this cache block for the first time, I'm the only owner of this cache block. So what state do I move to? What state do I move to? Exclusive, right? I read, I bring in the cache block. So if I do processor read, I am in the exclusive state. I will send the through the Snoopy bus. I will then make sure that everyone else know that I'm reading to it. This is when I first see this cache block. What will happen if I'm writing? From invalid. So from here, where do I go if I'm writing? If I see processor write. So if I see processor write, what do I go? Do I go to exclusive or do I go to modify? I'm writing, right? So the data is modified. So I'm will move here. If I see processor write, and you send signal to everyone else, say, hey, I'm modifying this data. With me so far? Are you with me so far? And if you are invalidated, if your cache block is not in the cache, and you see someone else is reading, someone else is writing, you stay at the same state, right? If you see someone else is reading or writing to that cache block, I don't care. I seriously don't care because I don't have that cache block. It's invalid anyway, so there's no point moving to any state. With me so far? Okay. So if I'm in the exclusive state and I'm reading, where do I go? I stay in the same state, right? If I'm reading to that cache block, I am the only owner of that cache block. I stay at the same place. And you don't have to notify anyone because no one has the data. If you write to the cache block from the exclusive state, where do you go? You are the only owner. You write to it. Where do you go? Yes. So basically you go to modify. Why? You modify the data through the write instruction, right? And then because you know that you are the only owner of that cache block, you don't have to send anything on a Snoopy bus at all, right? You don't need to use the bus. You are the only owner of that cache block. If you are in the exclusive state and you see someone else is reading, what do? Are you moving to M or E or S or I? You are originally you are the only owner, but then someone else tried to access that block. It means you are sharing, right? You're now sharing that cache block. So you move from E to S. So if you see someone else is reading from the Snoopy bus, what if you are the only owner and you see someone else is writing to the cache block? What do you move to? You have the block, but someone else modify it. Is it going to share or is it going to invalidate? The question is, do you have the most updated version of the data? I think that's a much bigger question. So you go here. If you see someone else is writing, you invalidate yourself because you don't have the most updated copy anymore. I don't have a copy. I will invalidate my cache block. If you are, so we're done with I and E. We're done with I and E. Let's go to, if you are in the modified state and you write, you stay at the same place. Don't have to notify anyone. You are the only owner of that block. You write to it. Yay. So just update the data. If you are in the modified state and you read, stay at the same place because the data is now dirty. You need to make sure everyone who might have the copy invalidated. If you're in the modify, you are in the modify state and someone else want to read that cache block, what do you have to do? Someone else want to read that cache block. If someone else want to read, first of all, you need to change to the share state because someone co-owns this data. The second thing you have to do is you have to flush. You have to flush because you need to give this data to someone else. The way you do this is give the data to the L2 cache where it's shared. Someone else can get and take that updated data, right? If you're in the modify and you see someone else writing to the data, where are you moving? If someone else is now writing the data, do you have the most updated copy? Yes or no? Someone else is modifying my address. Do you have the most updated copy? The answer is no, so you move back here. If you see someone else is writing. Okay, we're almost done here. Let's go to the case where you are in the share state. If you're in the share state and you read, you stay at the share state. Who cares, right? You are reading. If you're in a share state and you're writing, you move to the modify, right? Processor write and then send signal that you're writing so that everyone else can invalidate that cache block. If you're in the share state and you see someone else is reading, you stay at the same place. If you're in a share state and you see someone else is writing, you move to invalidate it because now your data is not updated. Any questions so far? So we are kind of done with this diagram. Okay, so if right now there might be no question, we will go and do an actual example. I think this is the best way you can learn how this is done. So from these PDF, before we take a break, what I want you to do is look at the question. All right, for some reason, I cannot move the window, so let me do this as quickly as possible. You see my PDF on the screen? Okay, so right now, this is, I know it's an in-class exercise. I don't want you to submit anything. We will go through this together. It will take some time. For now, just read the question. We'll take a quick break. Let's say we meet at 1:10. In the meantime, we resume at 1:10. In the meantime, please check out the question so we can start doing something with this particular question. All right? And feel free during the break time, go get coffee or whatever. If is the text big enough? Can you read the text on the PDF? Yes, no, I need a quick yes or no, so I need to either zoom in or not zoom in. So you cannot read the text. Let me put this on Canvas just in case, actually. I originally think I would just do it over here on the screen, but I think we might need Canvas, the files on Canvas so you can see it. So let me check what page is this. Page 10. So if you go to Canvas, you will see in class exercise 8 soon. That's words 10 point, no submit button, because everyone will get that 10 point because we are doing it together in class. I'm posting the PDF right now, so the file should be updated in a few seconds. Okay, I publish it. So can someone tell me whether you can see in class 8 or not? In class exercise 8. This is on Canvas. Oh my God, the text is still so small. Okay. Let me re-upload the files. You can use the old files, but it's still like pretty small. So I want to make sure the text looks better. I'm gonna go do that on my desktop. You can still work and go read the question. Again, because I use 5 minutes here, I'll shift the break to 1:15. Is that okay? Basically, we'll meet back at 1:15. Go check out the questions from in class 8. All right, so please go and take a look at it while you're taking a quick break. See you all in about 10 minutes, all right? All right. So I updated the files and hopefully it's a little bit more clear. Here is the question. Let me unshare the screen so I can move it on to my laptop so I can draw things on the PDF so that basically for you guys. So let me stop sharing and switch this over to this screen. Here. Okay, do you see my screen? Hello. Awesome. Let me mark up. So one of the very first thing for this question that you have to do is you are basically given 5 memory accesses, right? Over here, these are done through multiple processor P0, P1, P2, P2, and P3. They all share this 4-byte addressable processor. Each processor has 256-byte direct map write back L1 cache, a block size of 64 bytes. So with the block size of 64 bytes, and this is the first information, the second information. With the first and the second information, where is my index bits for my cache? So if you look at the address, right, what is the byte in block bit for here? For basically in this case, if there are 4 byte addressable, it means that I can only access each byte in 4 bytes chunk. I can go access byte 0, 1, 2, 3, 4, 5, 7, 8. I cannot access things like at byte 2, 3, 4, and 5. So my byte in block bits is going to be log of 64 divided by 4, which is what? Okay, so basically you are looking at a cache that has 64 byte block. How many bits are for the byte in block? What's the log of 64? What is log of 64? This is caching. Caching recap. Because we need to figure out where is the set ID. 6, right? So 6 bit. There are 4 sets over here, 4 sets, right? If there are 4 sets, how many bits is for the set ID? 2, right? Log of 4 is 2. So bit 7 and bit 8 is for the set ID. So this is the set ID. So what is the set ID of each of these addresses? What's the set ID of the first access? C is 1100, right? So what is my set ID? Is it 11? Is it 10? Or is that 00? I'm looking. Oh, my bad. This is bit 6 and bit 7. Bit 6 and bit 7. This is bit 0. What is the set ID? Bit 6 is right here, bit 7 is right here, so the set ID is 11, right? If you kind of forgot how to do this, go back to the caching lecture. Figuring out the set ID is essentially means that I have a log of the number of sets, and the bits that follows the byte in block is the set ID bit. What's the set ID of the second access where the last bit is 80? You need to look at this last 8 bit. What's the set ID of the second access? Come on. For the set ID, you just need to look at this. Oops. Can I erase this? Just need to look at. Oh, it's so hard to write it. You just need to look at the number that I highlight and figure out what is the set ID. So what's the set ID if that number is 8? Is it, what is the set ID? 10, yeah. How about the next one? 01, right? The next one is 00, the next one is 01. So this is going to set 3, set 2, set 1, set 0, and set 1. With me so far. Basically, the first request is going to set 3, second request go to set 2, third request go to set 1, fourth request go to set 0, and the last request go to set 1. Are you with me so far? So let's use a different color to specify whether this is a read or a write. Why is that the case? Read and writes are important for cache coherency. Is the first request a read or a write? It's a load. A load. For a load, am I reading or am I writing? Read, right? So the next one is store, so you're writing, reading, and reading. The last thing we have to figure out is what is the tag. What's the tag for the first request? What's the tag for the first request? The tag are the rest of the bits. So what is the tag? Let me just highlight the tag. Yes, so it's 0x110000. So the next one is again 0x110000. Notice that they go to a different set. It's just a trick question for you guys. The third one is 0x1f f f f f. The fourth one is 0x1f f f f f. The last one is 0x1f f f f. Any questions so far? Any questions so far? Essentially, the tag bits are this part. Oops. Basically the rest of the bits part. You have any questions so far here? All right, so I'm gonna fill in the table for the first one. For the first one, you have the load to R1, right? You have the load to R1. The load is to address 0x110000C0, right? So it means that, let me zoom in a little bit. Is this a little bit easier to see? Okay, so what do we have here? We have a load, right? We have a load to set 3. We have a load to set 3. If you look at set 3 at the final state, so this table show after all these 5 instructions, this is the state of my cache, right? After this 5 instruction, I have a load to, coming from processor 1. Processor 1 means that you look at cache 1. After this load, you will see that somehow you got an exclusive state. And this is your tag. So what does exclusive state mean? What does exclusive state mean? You went over this about 15 minutes ago. What does it mean to be in an exclusive state? What does it mean for my cache line to be in the exclusive state? What does exclusive mean? Yes, it doesn't have to worry about everyone else. You have the only copy of that cache block. How do you identify the cache block? You look at the tag, right? You look at the tag. If they match, you're supposed to have the only copy. So what else match? The only thing that match 0x110000 is cache 0 set 3, right? Because it has to go to set 3. That's the index bit. You have the same tag. You have invalidated state. If you are exclusive in the beginning, if you're doing a load, over here, right? If you're doing a load to this cache block, before this load, cache zero will not have the data, because if you're reading from it and you have the data, you're supposed to go to the share state. But somehow you go to invalidate. It means that originally you also in the invalidate state. Oh, my bad. Wrong box. We are looking at set 3. So invalidate state here. And with the same tag, 0x110000. Over here, you don't care because you just brought in this cache block. You only read it. So you don't know what is the tag because it's a previous cache block, and this can be in any of the state. because it's a different cache block. It is the first time you bring this cache block into set 3. If you look at cache 2 and cache 3, it's a totally different tag, right? This is a totally different tag. 0x10FFFF has nothing to do with this access. So you know by default, before all the 5 loads, everything here is supposed to look the same because it's a different, totally different tag. No one touch it. All right, so we are done with one access. We are done with this one. Any questions so far? Okay, so let's go through the second access. Second access is to what set? Second access store to R2 0x11000080. What set is this? It's on the PDF. I just wrote it to the right. What is the set ID? Two. Yep. So the set ID is 2. Basically, you're looking at it's from processor 1 again. So you're looking at this set. At the end of the day, you store. It's in the modify state. What does it mean? What does store and modify mean? It means I own this copy, and because it's a write instruction, right? It's writing to this data. It means that I have the only copy and the data is dirty. If you look at the other caches, cache 0 is the one that has a matching tag, right? And because it's a matching tag and it's correctly identify itself as invalidated, so you know that the tag here is supposed to be the same 110000. What is the state that cache 0 can take at the moment? It can be of any state, right? It can be of any state because I don't know what state I am. I saw someone writing to it. I'm gonna by default go to invalidated. So it can be M, E, S, or I. For the other set, the other cache, this set is having a totally different tag. So you know that it has nothing to do with this store. So you can copy it down here with the same status and the same tag 110000. Nope, I look at the wrong table. So there's 10FFFF modified 0x000000 invalidated. Any questions so far? Any questions so far? We are done with the second request. Because if you have question right now and you're not asking, it's gonna get more confusing as time goes on. All right, let's go through the fourth access. We'll skip the third and the fifth one because they go to the same address. It's a little bit more tricky. Let's do the load to R4. Load to R4. That's to set ID 0, right? So that's to set ID 0. It's from processor 2. Processor 2 load. My bad. It's from processor 1 again. It's from processor 1 is load to R4 with tag 1FFFFF. You see that it's in the share state. It means that if someone else has 0x1FFF, they're supposed to be in a share state. if you look at this, it means that cache 0, which happen to have tag, the same tag as the cache block we are reading, 0x1 FFFF over here from cache 0 can definitely be as in the beginning is in the share state, right? It can be in the exclusive state because I own the data and I have the only copy. It can also be in the modified state because I write the data. No one else has a copy until that load to R4 from processor 1. Processor 1 load to R4. I'm going to flush this cache. Processor 1 now has the most updated version of the data. Before this, I don't know what tag it has, and it can be in any state, MESI, in any of these states. I forgot to do this one as well. We have the store to cache 2. So before this, it can be in any of the state. All right. For the other two caches, you see that the tags are different. So you know that it's actually the same status down here. Now let's look at the problematic loads and store. You first store to that address followed by a load. What does store do? Store will invalidate everyone else. If you store followed by a load from P2, it means that P2 is now sharing with P0. And you can confirm this by looking at the state here. They are actually sharing. The tag looks the same, right? After that sequence of load and store to set 1, right, set 1, you see the same tag, the same state. The one that has this tag is invalidated. It means that it got invalidated probably because of the third store to R3. When you have a store, you modify the data, you have to invalidate everyone else. Because it has the same tag, you know this is going to be 0x1f, F. And when you have a store, it can be modifying from any of the state. So you can have M, E, S, or I here. Those are all possibility. If you look at these particular set from cache 0 and cache 2, right? You know that first you store from 0, then you load into processor 2. So because of this, you know that, hey, I don't even know what's in here because I might be replacing my block. It might be the block that I own already. So this is M, E, S, or I, M, E, S, or I. And lastly, this is a totally different tag. So I can copy it down here. And that's it for the question. Any questions? Because I feel confusion. And because no one say anything, I can't even begin to try to explain which part should I start. Oh, is this clear to everyone? How about this? Originally, I'm gonna leave this as like, okay, we do it together in class. Can you repeat the last one again? Sure, yeah. The last one meaning the third and the fifth request, right? So I'm gonna do it in a different color to make it a little bit hopefully more clear. So I've used blue ink. So you mean this one and this one, right? So if you notice, it's the same exact address, right? That's why I said this one can get a little bit tricky. What will happen if you store followed by a load to that same address? It means that the processor that do the store invalidate everyone. Are you with me so far? Basically, when you do a store, that invalidate everyone. You will be in a modified state, everyone else invalidated because you write to that. Yes, no, with me so far? If you are not with me, ask questions. Then after you're in the modified state, someone else want to read from it. It means that that guy will be in a share state. You will be in a share state because you will flush that updated value so that that person who want to load, who want to read the data has this updated value. So after these two instructions, processor 0 and processor 2 would be both in the share state, which you can see it from here. Share and share. Right? With me so far? Because you first do... okay, sure. So the store invalidate everyone. After you store, you do a load. It means that after you invalidate everyone, the other processor want to read it. It will go and get the correct version of the data. That's how cache coherency makes sure that you got the correct version of the data. You are invalid. From invalid, you do a load. The load give you the most updated version of the data. But now there are two owners. The owner is processor 0 who did the store and processor 2 who want to read the data. They will both have the same exact data. With me so far, right? Because there are two owners, both of them are not modifying anything, is both will be in a share state, which is reflect here. Both of them are share, right? Then after you establish this analysis, you know, well, let's get rid of the easier one first. Set one cache 3 is totally different tag, so it has nothing to do with this load and store, right? With me so far. Basically, set one for cache 3. It has nothing to do with this load and store, so you just copy this over to this. What you have to do now is you want to figure out, okay, what was in here and what was in here. Because you overwrite by doing a write and doing the read, you have no idea originally what's in here, right? That's why you put in X, because it might be the same cache block, but it might be a write to a different cache block. So the tag is unknown with me so far. And because of that, it can be in any state, right? Okay. Then you look at the last one, this one, and you know, hey, it's the same tag. So you know it's that address which got invalidated, which is correct, right? The first write will invalidate everyone. So that MESI state becomes invalidated. You know that it's the same tag, so you know you can write the same tag right here, right? But I don't even know what's the status of the coherence protocol state because that store invalidate everything. I can be in M state, E state, S state, or invalidated already. That's why in the MESI state, I have to put in M, E, S, and I. So are you with me for this last one? Okay, cool. Any other questions? So if there are no more questions, let me share a different screen. Let's stop sharing. and reshare my screen here to PowerPoint. So that's how the Snoopy protocol with the cache coherency work. One thing that I will change in terms of the in-class policy for this one, I now want you to submit something. I already did all the steps. You go watch the recording so that you can complete the rest of it and you submit your own answer. All right? Because I want to make sure you can go through this. It's going to appear somewhere. So make sure you can follow this and do it on your own. All right. The last slide that I want you to know is there's also another method instead of using a Snoopy protocol. This is called directory based. And it's pretty simple when you think about it. We are not going to go into like a detailed implementation of this, but instead of using a bus where everyone can probe, right, what is everyone else doing, you use a directory, which is basically is a table that keep track of the state of each cache block. And the policy is simple. For every single cache block, you store additional n+1 bit. This is additional bit. This bit, basically each local cache, let's say you have 4 processors, there'll be 5 bits. Each local cache will have the value of 1 if the block is in the cache. And then the last bit, this +1 bit, is for the exclusive bit. It means that, hey, there's only 1 copy. When you have a read, you set the bit from 0 to 1 if you have a read. If you have a write, you invalidate. Every single block will now become 0 except for yourself. And the cache can now update silently if the exclusive bit is set. And that's how the directory base works. These won't go onto your exam, but I want you to hear about it because this is another common policy that get used as you have to grow the number of processor. When you have more processor, more cores, it's not as scalable to use the Snoopy protocol. So this is another alternative. It's called directory based. It's actually track one cache per bit plus 1 more bit for the exclusive state. So that's it for the class today. If you have any questions, please do let me know. There'll be office hour tomorrow. There'll be another office hour on Monday. I want to make sure you can follow these logic because when I learn this for the first time, it's confusing for me. And I'm not sure how confusing it is for all of you, but if it is, I want you to kind of like sleep on it a little bit so that you know what question you want to ask. And please come and ask the question or just tell me to go through certain parts again. That's it for the class. I will send the PDF for the exam feedback, as I said, after I'm done with all the meetings today, likely sometime in the evening or tonight. I'm going to stop recording.